So, welcome to the second lecture of the module 1. What we have observed in the previous lecture, that in order to design a control, we need the information of present, past and future, and based on that PID controller comes into picture. We have also seen that present information is relatively more reliable than past and futuristic information. So, in this particular module, we are going to explore the control design using the information of the present and what kind of limitations or what class of the uncertainty that is actually compensated by the proportional control that we are going to explore in this particular module. So, purpose of the discussion to understand the role of present state information. In this lecture, I am going to tell you that what is meaning of a state in control design, and two classes of disturbance that is commonly defined in the course of the modern or nonlinear control, that is vanishing and non-vanishing. We are trying to understand their definition as well as how basically proportional controller can act whenever these kind of disturbances is acting on the system. We are also going to explore the limitation of proportional control, and during this investigation we are actually come up with very nice idea, that is the bondedness, stability and ultimate bondedness. It is possible to show that in practical situation one cannot able to compensate all kind of uncertainty, and due to that reason during the implementation most of time we are happy with the bondedness or ultimate bondedness of the behavior after applying some kind of robust control technique. Obviously, sliding mode control gives us some more attractive features, that is insensitivity with respect to match disturbance. What is meaning of match disturbance? Those kind of disturbance which enter through the control channel. So, if disturbance is bonded, so we can able to see that our system performance is insensitive with respect to that class of disturbance. We are going to talk about that in several subsequent lecture. And what is outcome? So, obviously one of the beautiful outcome of this course to understand the uniform bondedness and ultimate bondedness after applying the control system. So, we are talking about closed loop control system, and we are trying to also explore the limitations of the proportional control as well as some kind of variant of proportional control also I am going to discuss in this particular course, and after that we are trying to understand the need of the PI controller. So, let us start the second lecture. So, you can see here that I have already told in the previous class that I have to control a underwater vehicle, and our objective is very simple. Our underwater vehicle, I have to stop somewhere in between of the flow. So, underwater vehicle is moving in Ganga, so we have uncertainty and I have to stop that. So, this kind of problem is called a stabilization problem. In previous class we have also seen that suppose that if I have to track some kind of velocity, then we can convert that into tracking problem. So, in error coordinate frame that is converted into tracking problem, and due to that reason both problem is somehow equivalent, and due to that reason we are trying to solve some kind of simple problem that is called a stabilization problem. So, I have already designed the feed forward control in the previous class, and once you substitute the feed forward control, then whatever system you are getting, so that kind of system is represented by this. Now what is our objective? Our objective is to design this feedback control. Okay, what is meaning of feedback? It means that u should be function of v. That kind of things we have to design, and for simplicity I am assuming that the D disturbance is not present. Okay, and you can see that since I am just going to use the information of present, so I have scaled the present information by some number kp, and I am going to utilize this. And once you substitute this value here, since D is 0, so this is the closed loop system. So this system is called autonomous system. Why autonomous? Now you can see that in closed loop system, if you talk in terms of the block diagram, so I have input as a some kind of initial condition, and I will get some kind of Vt, and this guy is actually situated here. Okay, so basically there is no external interference, and due to that reason this class of system is called autonomous system. Now since I am assuming that velocity, that is just a scalar quantity, I have to move only on a straight line, that is our problem, and due to that reason I am going to represent the evolution of this velocity using this real line. Okay, now suppose that our initial condition V0 is positive. So if V0 is positive, so you can see that at each and every point I can able to calculate the rate of change of the velocity. What is that? So V dot is nothing but that become negative. Why? Kp is positive, V is positive, and due to that reason, due to this negative sign, now at this point V dot is less than 0. So what kind of things happens here? V is positive but V dot is negative, and due to that reason we will move in this direction. Let us try to see here in this in the left hand side of the real line. So here V is actually negative and Kp is already positive. So V dot nothing but positive, and what is positive direction? It means that I will move in the direction of the velocity. So it means that if V and V dot that is less than 0, so from the Newton's law I can always able to move in the direction of the decrement of the velocity. Okay, that is the observation. So it means that Kp I have to select positive. If I select Kp equal to negative, then what happens? You can just select Kp equal to negative, and if you are here, then Kp is negative, so negative negative that become positive, and this whole quantity V dot become positive. It means that I will move in this direction. Okay, so and we will converge towards the infinity. Similar kind of situation we have, we will move in this direction if Kp is negative, and due to that reason I can able to design Kp that should be greater than 0 if there is no disturbance. Okay, so in this way I can able to tune the proportional controller. You can see that several nice observation basically comes whenever you are giving the geometrical interpretation of this particular differential equation. Suppose now if you start from here, this is V equal to 0. So V equal to 0, it means that V dot also equal to 0. So for simplicity, you can just assume V as a some kind of quantity, position like quantity. Okay, V dot that is velocity like quantity, just you can assume. Okay, so now I can able to apply Newton's first law. So rate of change of some quantity equal to 0, so that quantity will remain in that state. So I have just very unique point, this point. If I start from this point, I am going to stay forever if there is no external disturbance, and that is the idea of the equilibrium point. So how to calculate the equilibrium point? If system is expressed in terms of the first order derivative, okay, So suppose that now I have system like x dot equal to fx, and suppose x contain x1 and x2, it means that that belongs to two dimension. So two dimension people are representing like that. Why? Because x1 is realistic measurement and x2 is the realistic measurement, means real number, some kind of real number comes into picture. So now here you can also see how to calculate equilibrium point. Just I am going to keep x dot equal to 0, because x is some kind of position like vector. So just I have to maintain velocity vector equal to 0, then I can able to apply the Newton's law and I will get the notion of the equilibrium point. Okay. Now what we have seen in the previous slide, that if I start from anywhere except this equilibrium point, I am going to converge towards this unique point where actually rate of change equal to 0. Okay. So same kind of things actually I have written here, that all trajectory are converging towards the equilibrium point. What is idea of asymptotic convergence? You might have in previous class I was talking about the asymptotic stability. You can see that what is physical interpretation of that. As you move towards the equilibrium point, what happens? Rate of change is going to decrease. Okay, and nearby of the equilibrium point, you can see that rate is very slow. So it requires infinite time to converge if you are the vicinity of the equilibrium point, and that idea is nothing but the idea of asymptotic convergence. And now if you have some kind of non-zero disturbance, obviously I don't have this kind of observation, I cannot able to preserve the equilibrium point, I don't have asymptotic behavior, asymptotic kind of behavior we are going to see in the next slide. Now what we have seen in this particular slide, that if I have to control some plant, so I have just scale our present information and then I have applied that present information here. So you can think, suppose that if I represent information in some other way, this is signum function, v greater than equal to 0, this is +1, v less than 0, that is -1, and then try to apply same kind of geometrical observation. Okay, whatever I have told, that is that I am telling Newton's law, because that is the consequence of Newton's law, that if some quantity and that their rate of change is opposite sign, then quantity will move in the direction of rate of change. Okay, so that kind of idea you can apply and do this kind of homework for the clear understanding that you can able to design proportional control, not like just what is classical proportional control is suggesting. You can free to select this kind of control also. Now here you can see that whenever we are talking about any system, I have already told you that continuity is one of the very beautiful property, and what continuity is telling, that if you have some system and if you have information of past and if you have information of present, then you can able to guess or somehow control the information of the future. Okay, and most of time what is our objective? I want to follow the velocity, I want to control the velocity. So somehow I am trying to control the futuristic value. It means that in order to apply continuity property, I need the information of past, and this notion of a state is responsible for that. Okay, so we are trying to understand what is meaning of the state. So I have taken very simple electrical system. During 10 or 10 plus 1 you have already learned about this. I have input and output, and now I have two switches, switch A and switch B. So system can switch between A and B. So if system at switch A state, you can apply Newton's law, and you can see that if I apply V, then I will get V by 2. But if you are at switch B switch position, at that time if you apply V, then you will get V by 4. Okay, so it means that for same input, and if internal condition is different, then you will get different output. Okay, so this idea is generalized for any class of system, and we have defined the notion of a state. So notion of a state of a physical system is any property of the object that relate input to output, such that the knowledge of input for t greater than equal to t0 and the state at t equal to t0 completely determine the unique output of the system. Okay, so that is the physical interpretation of the state in block diagram form. What we are telling that if you know the ut, if you know the xt0, that xt0 is nothing but all information from the minus infinity to t0, then you can able to get the xt. So this information, this is nothing but the state of the system. Now even if you do not have any physical system, you are working towards very abstract system, same definition is applicable. Now whenever you are dealing with any system, after application of control, you have already seen that I am talking about autonomous system. We, apart from autonomous system, generally after applying the control, another class of system that comes into picture, that is called non-autonomous system. So most of the engineering system is actually fall in the third category. Here I have written that is force system. What does it mean? That I have some system, I have some kind of input, and using this input I want to control the futuristic behavior of the system, and I am assuming that the information of a state is given at t equal to t0. Okay, so information of a state is nothing but information from minus infinity to t0. Okay, so now I have to design control based on the information of a state such that I will get the objective like stabilization or tracking. In previous class we have already learned about the stabilization and tracking. Okay, so now you can see that if you design u, that is function of x, then system either convert into autonomous system. What is meaning of autonomous system? There is no forcing function here, and time is not explicitly present, implicitly present. Okay, explicit means you try to understand implicit and explicit like this. Here first time independent variable is time, and then xt comes into picture, and based on xt I will get f. But here in order to get the rate of change of some quantity, explicit information of time is required. So here x came from somewhere, I do not worry about the time, but here I have to worry about the time. So that is the difference between autonomous and non-autonomous system. In this particular course, most of time I am going to talk about the autonomous system, because by designing control action, our system is going to convert into autonomous system. And now what is meaning of the order of the system? So you can see that that is coming from the geometry. So idea is you can able to represent 1 dimension, 2 dimension, 3 dimension, but how to represent n dimension? So in order to represent n dimension, even if you cannot able to visualize, just put n number of real number, so that correspond to the n dimension. So that kind of things we are trying to visualize using this. Now I have already told you that stability. Stability is one of the very crucial property, because somehow they are forcing us that if you know the past, if you know the present input, then how to actually characterize the behavior of the system. Okay, and due to that reason, now I have to specify the notion of stability here. In the first part of the discussion, what we have observed, that for the one dimensional system, if I start anywhere, okay, and if I design control based on proportional information, then I am converging towards the equilibrium point. And if there is no disturbance, then what happens? So I will converge in the vicinity of equilibrium point. I will not exactly converge to equilibrium point, because we have asymptote here. Okay, so I have this kind of stability is called asymptotic stability. It is possible to show that if some class of disturbance comes into picture, I cannot exactly converge to the nearby of the equilibrium point, but I will remain in this vicinity. Okay, so that idea, that if you start from the equilibrium point and if there is no disturbance, you are going to remain there. But if there is disturbance, then you are going to fall in the neighborhood of the equilibrium point if your system is stable. Okay, that is the idea, and due to that reason we have to understand the notion of stability. And in previous class I have already told you that notion of stability is inspired from the continuity. Okay, and how basically continuity comes into picture? That is coming from the concept of limit, left hand limit, right hand limit, and limit at that point. And whenever we are talking about limit, limit is nothing but some kind of mathematical macroscope. So in this particular system, what we have seen, I have given the initial condition if our system is autonomous, and after that we are actually looking towards the xt, because whatever control I have designed, that is function of the state, and due to that reason now autonomous system can be represented in this form. Now we also know that if I apply 0 input to this system, it means that if initial condition equal to 0, okay, it means that I am forcing something like this. So I am assuming that x equal to 0 is my equilibrium point. It means that if I give 0 as input, then I will get 0. So how to apply the notion of continuity here? What I will do, I will zoom xt and I will see the distance of xt from the origin. So xt minus 0. So this is symbol of the norm, okay, because I am assuming xt here as a vector. Okay, so whenever you are putting equality sign or inequality sign, so for inequality sign you have to convert n dimensional quantity into one dimension. So for that you have to use the notion of norm. Those who are not familiar with notion of norm, please just check anywhere in internet. You can able to see that how to calculate norm. One of the simple way to calculate norm by Pythagoras theorem, that if you have two quantity x1 square plus x2 square and square root of that, something like this. Okay, this is called 2 norm. Okay, so what basically we are going to do, I am going to zoom the output, and after that how to zoom the output. So you can see from this particular figure. So this is the equilibrium point, x bar, without loss of generality I can assume that is 0. So if you start from here, you can remains here if there is no uncertainty. But if you start in neighborhood of this, so you have several behavior. It might possible you will remains bonded, or you can able to converge to this equilibrium point, sometime with asymptotic speed, sometime with exponential speed. So based on that we have different notion of stability. So what basically we are going to do, first we are going to select the output ball. What is meaning of output ball here? Ball of xt, and due to that reason you can see that for all, this is symbol of for all, there exists a delta such that now what basically we are enforcing, that if you start from this ball of initial condition or input ball, so stability suggests that you can only you can able to remains on the output ball. Okay, so size of the output ball is depending on the application. Okay, what is meaning of asymptotic stability? I need one more extra condition, that is called the attractivity. What is meaning of attractivity? That as t tending towards 0, this condition should satisfy, means x t tending towards 0. So this symbol has more meaningful meaning, that xt, norm of xt is tending towards 0. So here we are talking about some kind of bondedness. Whenever we are talking about stability, here we are talking about convergence and bondedness, and exponential stability is talking about how fastly you are going to converge. So here rate of convergence is also associated. So these kind of concept is very fundamental in the nonlinear or linear control literature. So please go through that. Now I have taken the very simple example, okay, here. So you can also relate this with something like k p into vt. Okay, so I have just replaced vt by x and I have solved it. Okay, and after that I have applied the notion of epsilon and delta. Okay, so I have chosen epsilon, and if I choose delta equal to epsilon, then I can able to show epsilon and delta stability. So how one can show epsilon and delta stability? First you have to solve the differential equation, then you have to select a output ball, and after that you have to show that corresponding to output ball there exists a ball of initial condition or input ball. Similarly, you can able to show the asymptotic stability. first you have to show the stability and after that you have to show the convergence. And exponential stability, so you have to take absolute value, because here this is just one dimensional system, means xt belongs to R, but if we have xt belongs to Rn, means n number of state, at that time I have to take the norm here. Okay. So, if this kind of relation comes into picture, then our system is exponentially stable. It means that if you design proportional control for this system, then V equal to exponentially stable. Now, let us try to see the behavior in presence of the disturbance. You can see here that disturbance can be modeled in different way. So, suppose that if disturbance looks like this, what is meaning of this? That as V tending towards the 0, disturbance becomes 0. So, that class of disturbance is called vanishing disturbance. And if you have that kind of disturbance, it is possible to show that you can able to convert like this. What is signum V here? V greater than 0, that is plus, V less than 0, that is minus 1. Okay. So, now if you design Kp greater than equal to D sin V, okay, signum V multiplied by V, that will give us the mod V. So, if you design, and I am assuming behavior, just I am going to see the behavior on right hand side, because left hand side behavior is exactly same like the left hand side. Okay. So, you can see here that what happens, that if I select Kp and that is greater than the D0, what is D0? That is the, whenever we are calculating this kind of bond, if this is the case, then I have exactly similar kind of behavior. If I start here, V is positive, B dot is negative, you can just apply Newton's law. Okay. So, it means that if your gain is sufficiently large, then you can exactly able to compensate the vanishing uncertainty. So, conclusion observation is equilibrium point remains the same, because I can exactly able to converge to the equilibrium point, and at equilibrium point uncertainty is 0. So, equilibrium point remains preserved. All trajectory will converge towards the equilibrium point, provided this is the gain condition. So, if you have vanishing uncertainty, then you have to somehow estimate the uncertainty. So, using machine learning, AI also you can able to do these jobs. We have several different options. And asymptotic convergence still remains the same. Obviously, if D is non-vanishing, okay, then I cannot able to conclude the same. So, I have already defined signum function. So, you can see that if D not equal to 0, then what is our behavior? So, I am assuming that D not equal to 0 is represented by D0. Most of the practical system, this kind of disturbance comes into picture. You can just take example of the mobile robot. So, mobile robot is moving in the open environment. So, air is going to hit them, and you all are knowing that air is some kind of periodic wave. So, you can able to transform that wave in form of constant and sinusoidal function, and that is not equal to 0 at the equilibrium point. So, that is represent the non-vanishing disturbance. So, in presence of non-vanishing disturbance, you can see that even if you take any higher value of Kp, since D is non-zero, so at some point this disturbance is going to dominate. So, if you start far from the origin, you are going to converge, but if you are on the neighborhood of equilibrium point, what happens? Now, sign of V is positive and V dot also is positive, because disturbance, suppose that disturbance is positive. So, you have some kind of diverging behavior. If you are lucky enough that D is negative, then that will support, but most of time we have to do worst case analysis, and this is nothing but the idea of ultimate bond. Okay. So, what we have seen? We have seen that now whenever the non-vanishing uncertainty comes into picture, I cannot able to talk about asymptotic convergence. At that time, I have to talk about uniformly ultimate bondedness. So, next 4 to 5 minutes, I am going to brief you about what is meaning of a uniformly ultimate bond and how it is different from the ultimate bond. And now, whenever non-vanishing uncertainty comes into picture, then I have to explore different controller. So, I have to incorporate information of past also, and due to that reason we are going to explore the idea of PI controller. So, here you can see that I have, in order to illustrate the difference between bond ultimate or uniformly ultimate bondedness, I have actually taken very simple example. So, you can see that this system is affected by some kind of non-vanishing disturbance, and I have this kind of assumption. Suppose initial condition and D, some quantity I have D whatever that is associated with this disturbance, and if you solve this equation during your 10 plus 1 you have already solved using the exponent. Please do this exercise, and after that if you calculate the bond, it is possible to show, since exponential function is positive, A is positive, so it is possible to show that for all t this is less than equal to A. It means that in presence of this disturbance, Vt is always remains in some band, this is 0 and this part is either minus A or this is plus A. Okay. So, this kind of bond is called uniform bond because this is independent of the time. Now, it is possible to show that you can able to reduce this bond after some time. So, whatever bond we have calculated in previous case, so I have actually created from t greater than equal to t0 onward. It is possible to show that since exponential term is also associated with the solution, okay, so we haven't calculated the effect of exponential term because after some time this become less dominated, and due to that reason now it is possible to show this kind of inequality easily you can able to solve, okay, and so that Vt is less than equal to B after this time, and this time is always finite, okay. So, this is after some time, that is called transient time. So, once transient time is over, then we will actually converge to this bond, and this bond is nothing but the ultimate bond, okay. So, what happens that whenever we are starting some practical system, so initially we have more fluctuation, but after some time some dynamics will die out, and at that time we will get the true bond, and that is nothing but the ultimate bond, and these are the standard definitions that is existing in literature. You can check the Khalil book, okay, I have given the reference, okay. So, if you have generalized system, so this is non-autonomous system, so this is the definition. So, if there exists a positive constant C independent of T0, so this is very important because we are talking about uniform. If this relation will satisfy, then we are telling that your trajectory xt is uniformly bonded. How to do that? You have to solve the differential equation, and after that you have to check this. What is meaning of globally uniformly bonded? So at that time you are allowing any large value of A, and after that I have already told you that once your transient is die out, then you will get the true bond, and that is called ultimate bond, okay. So, here you can see that I need two constant, and after that I will select A, and that time is depending on A and B. In previous calculation, please check that finite time is depending on A and delta, okay, and after that you can able to establish this kind of relation. It means that I can calculate a finite time t, after that our trajectory is remains bonded. So, time information also I can able to provide whenever we are going to talk about the ultimate bond. This book is very good, extremely good in order to understand the linear as well as non-linear control system. So, now it is time to conclude the today's lecture. So, we have actually seen the effect of vanishing and non-vanishing perturbation. So, if I have vanishing perturbation, then proportional controller is good enough. There is no need to actually involve the information of the past, okay, because past information is sometimes dangerous. I have already shared that hacker can hack it. Uniform bondedness and ultimate bondedness concept we have seen, because whenever you are designing practical system, so most of time we are working with the ultimate bond, okay. And in next class I am going to explore the PI controller and what class of the disturbance that is going to tackle, okay. So, what is suggestion, my suggestion now, you can take any first order system, okay, even if second order system, and then you try to understand these concept, means what is meaning of vanishing, non-vanishing, uniform bonded and ultimate bonded, okay. So, in next class I am going to tell you that how to tune PI controller using the Newton's philosophy, same like the today's lecture. Thank you very much.